Welcome everyone to the June general meeting of the Kalamazoo Astronomical Society. It is fantastic to have you all here with us today on such an absolutely drop-dead gorgeous day. And I'm sad to say tonight ends our roughly 3-month streak of full houses. But again, that does not reflect on the quality of our speaker tonight, because I guarantee it is going to be an excellent presentation. So let's go ahead and jump right into it. Tonight's guest speaker has been a staff astronomer at the Carnegie Observatories in Pasadena, California since 2010. He grew up in Ann Arbor and earned a Bachelor's of Science degree in physics from Stanford and a Ph.D. in astrophysics from the University of California, Berkeley. His research spans all aspects of nearby, and I say, nearby galaxies, those within 100 million light years of Earth, which are nearby, I guess, including the oldest and youngest stars they contain, supernova explosions, and the production of the chemical elements. But its primary focus is investigating the evasive material that comprises most of the mass of the universe, dark matter. He currently lives in Sherman Oaks, California with his wife and 2 sons. So without further ado, please welcome Dr. Josh Simon.
Thank you, everybody. Richard, I think I need to be able to share my screen now. Okay. Thank you for that introduction, and thanks to all of you who are online with us today and have chosen to spend a little bit of your Friday evening listening to this. So I was hoping when Richard invited me last year that I might be able to come visit in person. As it has turned out, that didn't seem like the safest option. But I'm delighted to be able to share this with you online, and hopefully having it be a virtual presentation will enable more people to attend. So what I'd like to do in my talk this evening is tell you about galaxies. As Richard mentioned, my research at Carnegie Observatories focuses on some of the closest galaxies to us. The idea behind that is that these are some of the galaxies that we can observe the best because they're so nearby. Astronomically speaking, they're sitting right under our noses, just a few 100,000 to a few million light years away. And then we can use what we learn from these very nearby galaxies to make better extrapolations to the much more distant galaxies that make up most of the universe, but that we can't see in nearly as much detail. What I'll particularly be emphasizing is not just the part of galaxies that we're all familiar with, the stars, but also the hidden side of galaxies, which is made up of a mysterious substance called dark matter that turns out to be far more important to galaxies than the stars are. One of the key goals of the next generation of telescopes that are currently under construction, which I'll tell you a little bit about, is to reveal new clues to exactly what this dark matter might actually be. So I'll begin by giving you an introduction to galaxies. I'm sure that most of you are already familiar with what a galaxy is, but it's always good to start off on some common ground that we're all comfortable with. And besides, this gives me an excuse to show you a bunch of pretty pictures, which of course is half the point of astronomy anyway. Then I will I'll introduce you to the local group of galaxies where our Milky Way is located and some other interesting galaxies in our cosmic neighborhood. In the second half of my talk, I'll tell you about dark matter, and in particular, one of the theoretical problems related to the study of dark matter that astronomers, including me, have been wrestling with for about the last 2 decades. So to start off, let's start at the beginning. What is a galaxy? Well, as the source of all knowledge, Wikipedia tells us a galaxy is a group of stars and gas that's held together by its own gravity. Galaxies come in an enormous variety of different shapes and sizes. So I think the picture that we all tend to have in our heads of what a galaxy is something like this grand design spiral galaxy that you can see in the lower right. But not all galaxies share that basic structure. There's another class of galaxies called elliptical galaxies, which you can see an example of up here. Elliptical galaxies are much less photogenic than spiral galaxies. They don't have any spiral arms. They're just kind of the same dull yellowish color all over. They don't have the variety of colors that spirals do. And just their light is very smoothly distributed. But astronomers still find elliptical galaxies interesting for a couple reasons. First of all, most of the very biggest galaxies in the universe are ellipticals. And also, most of the largest black holes that have been discovered to date are found at the centers of giant elliptical galaxies. Now, to give you a sense of scale on these images, these two galaxies are very roughly a couple 100,000 light years in diameter. And that's comparable to the size of our own Milky Way. But not all galaxies are this big. There's another class of galaxies known as dwarf galaxies because of their small sizes. So the counterparts of giant elliptical galaxies, when you get to the dwarf galaxy regime, are dwarf ellipticals, as you see here. This galaxy looks a lot like the giant elliptical I just showed you, except that it's much smaller. It's only about 20,000 light years in diameter instead of nearly 250,000. And then the counterparts of spiral galaxies in the dwarf galaxy mass range are known as dwarf irregulars. So when a galaxy is significantly smaller than the Milky Way, it's not able to form and maintain the beautiful spiral arms that many galaxies have. And instead you end up with these galaxies that kind of look just like a train wreck, hence the name irregular. Okay, so in terms of the shapes of galaxies, they can be spiral, elliptical, or irregular. And then the physical properties of galaxies can really span an enormous range. So in terms of a mass, the smallest galaxies weigh about 1 million times as much as the sun, whereas the largest can be as much as 10 trillion solar masses. The brightness of galaxies similarly covers a huge range from 1,000 times the luminosity of the sun for the very smallest dwarfs, up to 1 trillion solar luminosities for the biggest giant elliptical galaxies. And then in terms of their physical extent, the most compact galaxies are just about 100 light years across, whereas the biggest can be as much as 300,000 light years from one end to the other. So what accounts for these tremendous differences between galaxies? Well, one factor is simply size, how much material a galaxy was able to accumulate as it was forming. But we've already seen that can't be the whole story, because I've shown you galaxies that were of similar size but look very different. So the other main factor that contributes to the appearance of a galaxy is whether it contains any cold gas. And the reason this is important is that cold gas is the fuel from which new stars are formed. So spiral galaxies and irregular galaxies still contain significant amounts of cold gas. They're still forming new stars today. In our Milky Way, about one new star on average is formed every year. On the other hand, elliptical galaxies have used up most, if not all, of their cold gas. So they're no longer forming any stars. That's why they look so smooth and boring today. Now, I don't want to go into too much detail here because star formation could easily be its own entire lecture. But just to illustrate for you the effect that the formation of recent stars can have on the appearance of a galaxy, here's an image of the Whirlpool galaxy, M51. And you can see these series of red knots that trace out the spiral arms of the galaxy. If you could zoom in on these, what you would see is something like this. You've got a cluster of very bright, hot blue young massive stars that has just formed. And when it forms, it's surrounded by a cocoon of gas and dust. And then over time, so this cluster is a few million years old, the fierce winds from those young stars blow that cocoon of gas and dust away. You can actually see that happening. You can see the winds pushing this gas away from the cluster along this edge here. And so what you're left with, once those winds have been blowing for 10 or 20 million years, is the gas surrounding the cluster is all gone, and you just have the very bright blue light from the cluster. And that's why the spiral arms of galaxies appear blue. All right, so that covers the basics of galaxies. Now let's talk a bit about what galaxies are made of. So of course, galaxies have stars in them. That was part of our initial definition after all. But it turns out that when you do the counting, stars add up to just about 10% of the mass of a typical galaxy. All right, so what else is there? Well, I just got finished telling you that gas is an important component of galaxies. However, in almost all galaxies, there's much less gas than there is stars. So in most cases, even though the gas can have a dramatic effect on the appearance of a galaxy, it only represents 1% or at most a few percent of the total mass of the galaxy. Galaxies also contain dust. So you can see the dark band cutting across the middle of the Sombrero galaxy here. That's from a thin layer of interstellar dust. But even though dust is very effective at blocking some of the light from galaxies, it takes a really tiny amount of mass in dust in order to accomplish that. And so the amount of dust in galaxies is much smaller even than the amount of gas. So now we've added up the parts of the galaxy that we can see, and we're still at just a little bit over 10% of the total mass of the galaxy. So what is the rest of it? Well, the other 89% of a galaxy is made up of this strange substance called dark matter. I'll go into substantially more detail on this a little bit later on. But for now, I'll just say that dark matter is a completely new form of matter that's never been seen before, and it doesn't give off any light, which obviously makes it a bit of a challenge for us to investigate. All right, so now let's go over some of the galaxies in our cosmic neighborhood. So here's an image of our Milky Way. And I think that even if this one picture were the only thing that you had to go on, it would be obvious that our Milky Way is a spiral galaxy rather than an elliptical. So we can see that it contains substantial amounts of dust and gas. And moreover, the light from the galaxy only covers a small band across the sky. So spiral galaxies, even though they can be very big across, hundreds of thousands of light years, they're also very thin, maybe just a few thousand light years from top to bottom. So you can think of the three-dimensional structure of a spiral galaxy as something like a frisbee, a plate, for the older members of the audience, a record or CD, whatever your favorite round flat object is. And so you can imagine that if you're sitting within such an object and looking up at the sky, you're only going to see that covering a small portion of the sky. On the other hand, if we lived in an elliptical galaxy, then we would see the galaxy filling up the entire sky, which would be a very, very different experience. If we could go up above the Milky Way and see what it looked like from a more face-on perspective, we think it would look something like this. So there's a bar at the center of the galaxy. It has a couple of main spiral arms, and our sun is located just kind of in between some of these spiral arms, about 25,000 light years away from the center. Most galaxies like the Milky Way live in small groups of other galaxies. So here's an example of such a group. This group has 3 spiral galaxies located in the constellation of Leo, and it's therefore known as the Leo triplet. Now, like the Leo triplet, the Milky Way is also located in a group of 3 spiral galaxies, which is known as the local group, as I'll show you in a minute. For completely unrelated reasons, it turns out that my younger son is also named Leo. Fortunately, he turned out not to be triplets, or I think my wife would have been pretty upset with me. So as I mentioned, the Milky Way is located in a group of 3 galaxies. Because astronomers are not very creative at naming things, this group is called the local group. And so the other major galaxies in the local group are M31, the Andromeda Galaxy, and M33. So let's take a couple, and then the rest of the local group, it consists of this menagerie of about 100 dwarf galaxies. So let's take a look at some of these other members of our local group. So here's a better view of the Andromeda Galaxy, M31. This is another large spiral galaxy. We think it's quite similar to our Milky Way. It's a little bit bigger. It's not forming quite as many new stars anymore. But on the whole, its properties are quite comparable to those of our galaxy. And it's located about 2.5 million light years away from us. This is M33, the Triangulum Galaxy, which is a smaller spiral galaxy. It's only about 1/10 the size of the Milky Way and M31. It's also located about 2.5 million light years away from us. And what's particularly nice about M33 is that it's oriented much more face-on to us. So we can get a much clearer view of its overall structure relative to the Milky Way or M31, which are seen more edge-on. And unlike the bigger spiral galaxies, M33 seems to have very few or perhaps no dwarf galaxies orbiting around it. So here's a kind of a 3-dimensional cartoon of the local group. We have the Milky Way up here near the middle, Andromeda with M33 right next to it over in the lower right, and then clustered very tightly around each of these big spiral galaxies are groups of dwarf galaxies. There are also a few much lonelier dwarf galaxies off by themselves in the outskirts of the local group, but most of the dwarfs tend to be located very close to one of the big galaxies that they're orbiting around. All right, so now let's take a look at some of these dwarf galaxies. So this is an image of the 2 brightest and biggest dwarf galaxies orbiting the Milky Way, the Magellanic Clouds. This picture was taken from Australia, just looking up at the sky at sunset. And you can see these 2 fuzzy objects here. These are the Magellanic Clouds. The bigger of the 2 is known as the Large Magellanic Cloud, again, illustrating our lack of creativity, and you'll never guess what the smaller one is called. All right, you probably figured it out. So up here is the Small Magellanic Cloud. Now, if you've ever visited the Southern Hemisphere, you've probably seen these galaxies in the sky. They're so bright and so nearby that they're easily visible to the naked eye. You might, however, not have realized that the glowing cloud up above the horizon was actually an entirely separate galaxy. Now, the reason that these objects are named after Ferdinand Magellan is that he was the first Westerner to leave us a record of their existence, which he made note of on his ill-fated attempt to circumnavigate the globe. Now, of course, Magellan doesn't really deserve credit for discovering these objects. Their presence was perfectly obvious to everybody who lived in Africa, South America, and Australia for thousands of years before he came along. But those people didn't happen to leave a written record that was passed back to Europe, and so today we still remember Magellan as the namesake of these objects. Here's a closer view of the Large Magellanic Cloud. I think it's obvious that this is a dwarf irregular galaxy. It's almost big enough to be a spiral, and if you squint a little bit, you may be able to make out just some hints of spiral arms. So one over here, and another one coming off the edge of the bar in the lower right. Obviously this is not the sort of grand design system like the Whirlpool and M33. The Large Magellanic Cloud is about 1/10 the size of the Milky Way. It's the closest bright galaxy to us. It's located about 150,000 light years away. You can see a variety of nebulae in the galaxy from stars that have recently formed. Its smaller neighbor is the Small Magellanic Cloud, which you see here. This is another dwarf irregular galaxy. It's about 1/3 as big as the Large Magellanic Cloud. It's a little bit farther away also, about 180,000 light years from us. In this image on the left of the SMC, I'm showing you the stars in the galaxy. The image on the right shows the ionized gas. So this is gas that has been heated up from the formation of massive young stars recently. And what happens every time a group of young stars form, as I showed you a little bit earlier on, is they blow a bubble of hot gas surrounding them. And I think that you can see these bubbles more clearly in the SMC than any other galaxy that I know of. And so I just think this picture is so cool, and I couldn't resist showing it to you guys. Here is another dwarf galaxy in our local group, NGC 6822. This is a smaller dwarf irregular galaxy. It does still form some new stars. You can see, again, the bubbles of hot gas in it, but it is smaller and less active than the Magellanic Clouds. And then most of the dwarf galaxies in our local group look more like this. So these are really tiny systems. This one is called Leo 2, the second dwarf galaxy found in the constellation Leo. They consist of a few 100,000 to a few million stars. They're very old. They formed all their stars 10, 12, 13 billion years ago. They don't look very impressive, but they turn out to be quite interesting objects, astronomically speaking. Now, one nice connection for me personally between my research and Carnegie Observatories, the institution that I work at, is that the first dwarf galaxies to be discovered outside of the Magellanic Clouds, which of course were known for thousands of years, were discovered by astronomers who either were at the time or had previously worked at Carnegie and at the Mount Wilson Observatory, which is owned by Carnegie. So the first two dwarf galaxies orbiting the Milky Way discovered were Fornax and Sculptor more than 80 years ago. Those were found by someone you may have heard of, Harlow Shapley, who had started his career at Carnegie and Mount Wilson. By this time in 1938, he had moved on to become the director of the astronomy department at Harvard. The next two dwarf galaxies, Leo 1 and Leo 2, were discovered by another Carnegie staff member, Albert Wilson, and a colleague at Caltech. And then the third pair, these seem to always be discovered in twos. Draco and Ursa Minor were again found by Wilson a few years later, although by that time he had actually moved on to become the director of Lowell Observatory in Arizona. So the discoverers of these dwarf galaxies and the staff of the Mount Wilson Observatory, you can see played a significant role in becoming leaders in the astronomical community throughout the course of the 20th century. All right, so I think we've covered galaxies and our local neighborhood around the Milky Way. So let's get on to dark matter. Now, as I mentioned, dark matter is a strange substance. It doesn't give off any light. And that is a bit inconvenient for those of us who are trying to make a living by studying the light given off by celestial objects, that most of the universe consists of something that we can't see. But as I'll show you, the observational evidence for the existence of dark matter has become quite strong over the past number of decades. And so, the large majority of astronomers is quite convinced that that dark matter must be real. And what we're left to do here is try and use our biggest telescopes to figure out what dark matter actually might be. All right, so the first question that you probably want to ask about dark matter is, if we can't see it, if it doesn't give off any light, how can we really be sure that it's actually there? Well, we know that dark matter is present in galaxies because we can detect its gravitational influence on the stars and the gas in galaxies, the parts of the galaxy that we can see. So the way this typically works is spiral galaxies are rotating. So that means that if you're looking at a spiral galaxy, then one side of the galaxy is always moving towards you. The other side of the galaxy is always moving away from you. And when in that kind of physical situation, we can use the Doppler shift to tell us how fast the galaxy is spinning. So the light from the side of the galaxy coming towards you is shifted towards bluer wavelengths a little bit. The light from the side of the galaxy moving away from you is shifted towards redder wavelengths. And so the difference in the wavelength between the two sides of the galaxy tells us the speed at which the stars and the gas in that galaxy are moving. And then just as we can use the speed at which the Earth is orbiting around the sun to tell us how much the sun weighs, we can use the speed at which stars and gas orbit around the center of a galaxy to tell us how much a galaxy weighs. Okay, so that gives us a way of measuring the mass of a galaxy. And it's pretty straightforward to determine the number of stars in a galaxy. We can just take a picture of it and start counting. We understand stars reasonably well, so it's also not hard to estimate what the total mass of those stars is. And what we find when we compare those two numbers is that galaxies weigh about 10 times as much as all of their stars put together. So it's as if I woke up one morning, stepped on my scale, and it told me that I weighed 1,500 pounds. Now, the first thing that I would probably think is that I better go out to Target and buy myself a new scale. But if I tested out the scale by putting some things whose weight I knew on it and found that it was actually giving me the right answer, then I'd be forced to conclude that there isn't anything wrong with the scale. And there must be something providing most of the weight on the scale that I can't see. And in the case of galaxies, that something is dark matter. All right, so the next question that I think you're going to want to ask me is, what is dark matter? It turns out that it's a little bit easier to start with the opposite question: what isn't dark matter? So the first thing that most people think of when they hear the phrase dark matter is that it's referring to black holes. We're pretty sure at this point that dark matter is not, in fact, made of black holes. There is a small possibility of black holes of a very particular mass that hasn't been completely ruled out yet, but almost the entire mass range of black holes has been excluded as making up dark matter. Dark matter is also not made up of faint stars like brown dwarfs, white dwarfs, neutron stars. It doesn't have any connection to the products of stellar evolution. In fact, we think that dark matter must be something fundamentally different from ordinary matter, by which I mean atoms and molecules, the stuff that we're all familiar with. Instead, we think that dark matter is a new kind of subatomic particle that's never been seen before. So you could think of this as a little bit like the Higgs boson, which was discovered at the Large Hadron Collider in Switzerland about 10 years ago. And that discovery was very quickly awarded the Nobel Prize in Physics in 2013. So the properties of the dark matter particle are probably not identical to those of the Higgs boson. It has a different mass, most likely, And it may have some different quantum characteristics as well, but conceptually, you can think of it as the same sort of thing. Now, what is different about dark matter compared to the other particles that we know of, protons, neutrons, electrons, and so on, is that it doesn't interact with ordinary matter in any way except through gravity. So let me give you an example to illustrate what I mean when I say that it doesn't interact. So imagine that I get shrunk down like Ant-Man, except instead of stopping at insect scales, I keep going all the way down to atomic scales. So now I'm wandering around, surrounded by atoms and subatomic particles. And I happen to see a neutron sitting next to me. So just for fun, I pick up my neutron and throw it against an atomic nucleus that I see across the room. So I've got pretty good aim. My neutron scores a direct hit on the nucleus. And now there's a couple different things that can happen. So the neutron could bounce off. So it goes one direction, the nucleus goes the other direction. It could stick to the nucleus and turn it into a different isotope of whatever element that nucleus was. Or if it was a particularly big nucleus, then the neutron can split it into pieces. And so that's how, for example, a nuclear reactor works. Now let's say that instead of picking up a neutron, I pick up a dark matter particle. And again, I throw it at my nucleus, hits it dead center. But now, instead of bouncing off or sticking or breaking the nucleus up, something different happens. The dark matter particle just keeps right on going, doesn't even notice that there was a nucleus there. And similarly, the nucleus has no idea that anything just ran into it. It stays there and nothing happens to it. So dark matter doesn't feel electric or magnetic fields. It doesn't emit any light. The only thing it can do is pull on stuff with its gravity. All right, so that's what we think dark matter is. And over the past 3 to 4 decades, theoretical astrophysicists have been busily working on trying to come up with a theory of dark matter that explains as much of the universe as possible. And so the best theory that has been developed over that time is known as cold dark matter. So in this cold dark matter model, you can run simulations of the evolution of the universe, the evolution of galaxies. And this theory has been remarkably successful at explaining almost everything that we see out there in the universe. It explains the distribution of galaxies through space, explains the cosmic microwave background radiation. It explains the expansion of the universe. But there's a few things that it hasn't managed to correctly predict so far. And if you look at the history of science, sometimes it's tugging on exactly those sorts of nagging little loose ends that unravels an old theory and points the way to a deeper understanding of nature. And so one of the key focuses of astronomers over the last 20 years since these potential problems were first recognized has been trying to investigate them in as much detail as possible to see whether they are really telling us that there's something basic wrong with our cold dark matter theory that generally seems to work so well, or if there may be a different theory that can explain the observable universe even better. And so one of those nagging issues in the case of the cold dark matter theory is that the theory predicts that galaxies like our Milky Way should be surrounded by huge numbers of much smaller dwarf galaxies. So in the case of a galaxy the size of the Milky Way, we expect it to have hundreds, perhaps as many as 1,000 dwarf galaxies orbiting around it. Now the problem is that after decades of searching for dwarf galaxies, as of early in the 21st century, we had only managed to find 11 of them. So this seems pretty bad. Not only do we have no idea what 90% of the universe is made of, now we can't find 99% of the galaxies that are supposed to be there either. So this drastic mismatch between the expected number of dwarf galaxies and the observed number became known as the missing satellite problem. And that led us to wonder whether it's possible that there could be large numbers, hundreds of undiscovered dwarf galaxies orbiting the Milky Way that hadn't been spotted yet. Now, to show you how this problem came about and to show you what we're doing about it, I need to take a step back for a minute and go through the process of how astronomers actually discover dwarf galaxies. So historically, dwarfs were found by looking by eye at photographic images of the sky. So beginning in the 1950s, at the Palomar Observatory in California, photographic plates covering the entire night sky were taken. And then the astronomers who were interested in finding dwarf galaxies would sit down, literally with a magnifying glass, and pore over these plates inch by inch, looking for a fuzzy cloud of stars that could be a new galaxy. So people, non-astronomers often think that discovering a new galaxy is something really glamorous. People are always asking me if I've found a new galaxy. But in fact, it was incredibly painstaking and tedious to do. And just to add insult to injury, the dwarf galaxies that you can find with this technique are not even that hard to see. So here I'm showing an example of Palomar Sky Survey images, one of which has a dwarf galaxy in it and one of which does not. And I think it's pretty obvious. You can see the cluster of faint stars at the center of this image and nothing similar in this one. So it's not even that these dwarf galaxies are that difficult to spot. It's just that the sky is a really big place. And so it helps a lot if you know where to look. Now, so as of around the year 2000, astronomers had carefully searched the entire Palomar Sky Survey data set. And as I mentioned, had only found 11 dwarf galaxies, the 2 Magellanic Clouds plus 9 new systems over the span of many decades of searching. Now, what has changed this picture over the last 2 decades is the advent of digital sky surveys. And the first of these was the Sloan Digital Sky Survey, which launched in 2000 and released its first results around 2005. Now, these modern digital sky surveys have 2 major advantages over the Palomar Sky Survey. So first of all, they use digital detectors, CCDs, instead of photographic plates to gather the light. CCDs are about 100 times as sensitive to light as film is. And so that means it's possible to detect much fainter stars with them. And second of all, the data from sky surveys now are stored digitally rather than on prints of photographic plates. So instead of trying to use a magnifying glass to discover dwarf galaxies, you can simply download a catalog of all of the hundreds of millions of stars detected by one of these surveys, and then write a computer program to search through that catalog of stars for possible dwarf galaxies. So this is much less romantic, of course, but also vastly more efficient. And it enables us to detect much fainter dwarf galaxies. So again, I'm showing you here 2 images from modern sky survey data, one of which has a dwarf galaxy in it, and one of which doesn't. But this time, we're looking at much fainter dwarfs, so faint that, in fact, you can't see them at all in these images. But if I show you the results of a simple computer program that measures the density of faint stars across these images, then you can clearly see that there's an excess of faint stars right at the center of this image here, and nothing at all in the other image. And so this is exactly the signal that we expect to see for a very faint dwarf galaxy. Okay. So now let's consider where things stand after 15, almost 20 years now of these digital sky surveys. So as I told you a little while ago, from the photographic sky surveys, we were only able to identify 11 dwarf galaxies. From 2005 to today, with the Sloan Digital Sky Survey, the Dark Energy Survey, and other surveys, we've now found 46 new dwarf galaxies orbiting the Milky Way. So this is a really major improvement on where we were at the beginning of my career. We've got a factor of 5 more satellite galaxies orbiting the Milky Way to study, which has been great. However, it's also still rather drastically short of what our theory tells us could be out there. So there may be as many as 950 dwarfs out of our predicted 1,000 that still haven't been identified. And our digital sky surveys have currently covered most of the sky. So while we think that there's still a little bit of remaining area that we're actively looking at, but to the depth of the current surveys, it looks like not much more than the 57 galaxies shown here are going to be found. So that makes us wonder whether it's possible that there could be even fainter dwarf galaxies that even in the latest surveys are still invisible and can't be detected. The only way to determine that is going to be with even deeper sky surveys, which are going to begin in the next year or two with the Vera Rubin Observatory, which is currently under construction in Chile. So the Rubin Observatory is going to be an 8-meter telescope, and it's going to have the largest camera ever constructed. I'm showing a picture of one of the lenses for the camera here with technician for scale. So this is going to be a 3,200 megapixel camera. And this enormous camera plus a very large telescope is going to, it means that the Rubin Observatory will be able to image the entire sky vastly more rapidly than any previous telescope, and also more sensitively. So the plan for the Rubin Observatory is that over a period of 10 years, it's going to repeatedly image every part of the sky that's visible from Chile. And that will enable us to do a couple of really unique things. So first of all, you can combine those hundreds of images at any given point together and make a movie of what the sky looks like, and watch for example, variable stars, transient events like supernova explosions, moving objects in the solar system like asteroids. And then the other thing you can do is you can take all of those hundreds of images and add them together. And that will make what's effectively the deepest image that you can get of the night sky from a telescope on the ground. And so this incredibly deep co-added image from the Rubin Observatory is exactly what we need in order to try to detect the faintest possible dwarf galaxies. Now, the challenge that we're going to have once the data from the Rubin Observatory start coming in is in telling what is a dwarf galaxy and what isn't. So back in the days when the dwarf galaxies that we're studying looked like this, it didn't take a whole lot of expertise to say, oh yeah, that looks like a dwarf galaxy. Now that we're in the regime where we're studying dwarf galaxies that instead look like this, it takes a lot more work to tell whether a group of faint stars that you see is in fact a dwarf galaxy or not. So in order to see how we're going to accomplish that, we need to go back to our original definition of a galaxy. So remember I said that a galaxy is a group of stars and gas held together by its own gravity. It turns out that what's been realized over the last several years is that we actually need to add a new criterion to this definition. and that is that a galaxy contains dark matter. So every galaxy that we know of, with possibly one or two exceptions that are still a bit controversial, contains significant amounts of dark matter in it. And in contrast, all the other stellar systems, star clusters, and so on, that we know of have no detected dark matter at all. So it's really the dark matter that sets a galaxy apart from other kinds of groups of stars. So in order to tell whether a candidate dwarf galaxy has any dark matter in it, what we need to do is measure the velocities of the stars, see how fast they're moving. The reason for that is, as we discussed before, dark matter, because it comprises most of the mass of a galaxy, also is responsible for most of the galaxy's gravity. The more gravity the galaxy has, the faster it pulls all of its stars around it. So to give an analogy for this, if I were an astronaut and I went up to the moon, so I'm standing on the moon, now I jump up in the air. An astronaut on the moon can jump very high and will come down very slowly because the moon is not very massive. It doesn't have very much gravity. On the other hand, if we could send an astronaut to a much more massive object, let's say Jupiter, ignoring, of course, the fact that Jupiter doesn't have a surface for the astronaut to stand on, an astronaut jumping on Jupiter would get pulled down very rapidly and would not be able to jump very high because Jupiter's much greater mass creates a stronger gravitational pull and pulls the astronaut back down much harder. So we can use effectively the same test in candidate groups of faint stars found by the Rubin Observatory to see whether they're dwarf galaxies. The challenge is going to be that the stars in these systems, as I've shown you, are very faint. So the only way to accurately measure their velocities is going to be to use our largest telescopes. Today, that would be, for example, the Keck telescopes in Hawaii, the Magellan telescopes in Chile, and in the future, it will be the even bigger telescopes, the 30-meter telescope, the Giant Magellan telescope, that are currently under construction. And so here's an example of what we might see when we start examining all of the groups of faint stars that are detected by Rubin. So if we're looking at a system that is not a dwarf galaxy, doesn't have any dark matter in it, it is not very massive, then we would see the stars moving around at very slow speeds, 0.5 kilometer per second, just 1,100 miles an hour, practically a snail's pace. On the other hand, if we're looking at a system that is a dwarf galaxy, it has lots of dark matter in it and much stronger gravity, making the stars move much faster, we'll see them moving at typical speeds of around 5 kilometers per second or 11,000 miles per hour. So by combining observations with the next generation 25 to 30 meter telescopes to study the candidate dwarf galaxies that are discovered by the Rubin Observatory, we will finally be able to come up with a complete census of how many dwarf galaxies there are orbiting the Milky Way, and thereby test our theoretical predictions from the cold dark matter model. But there's a possibility that we could end up in what's kind of a nightmare scenario for astronomers who study dark matter. What if some of these hundreds, 1,000 dwarf galaxies that are supposed to be out there never formed any stars at all? What if they're just naked clumps of dark matter silently orbiting around our galaxy? Then, how can we possibly tell if they're actually out there, as our theory predicts, or if they're not, and the theory needs to be revised? Well, it turns out that particle physicists have recently come up with a possible solution to that problem. And so you probably know that if you combine matter and antimatter, then they annihilate with each other and produce a burst of gamma rays. Gamma rays are just extremely energetic photons. They're like X-rays, but with even higher energy. So a gamma ray can have 1,000 times the energy of an X-ray. So for example, if you have a proton and an antiproton that collide into each other, then they turn into this, this pair of very energetic gamma rays. So it turns out that dark matter can actually do the same thing. And you don't even need to invent anti-dark matter in order to accomplish that, because in most of the particle theories of dark matter, a dark matter particle and an anti-dark matter particle are actually the same thing. So all that has to happen is that any two dark matter particles bump into each other, and boom, you get some gamma rays. And the great thing about gamma rays, unlike dark matter particles, is that we can actually build telescopes that can detect them. So in fact, we have an excellent gamma ray telescope in orbit right now, the Fermi Space Telescope, which was launched about 15 years ago. And so in principle, the Fermi telescope could detect gamma rays coming from dark matter particles annihilating themselves. So here's a map of the sky as seen by the Fermi telescope. This bright band across the middle of the image is the glow of the Milky Way, which is present in gamma rays just as it is in photons at every other wavelength. And then most of the emission that you see above and below the Milky Way comes from the supermassive black holes at the centers of very distant galaxies. Now, what's particularly exciting is that over the last several years, astronomers have detected more gamma rays coming from the center of our Milky Way, where there should be the greatest concentration of dark matter, than they expected. And then they can account for with the things that we know of that are producing gamma rays. And so there's been periodically bursts of news coverage suggesting that the extra gamma rays coming from the center of the Milky Way might be our first detection of dark matter. Now, the problem is that the center of the Milky Way is an incredibly complicated place, especially for gamma ray astronomers. So it's filled with all sorts of things other than dark matter that are also producing gamma rays. So for example, the center of our galaxy contains a supermassive black hole. The first picture of this black hole was released a few weeks ago by the Event Horizon Telescope collaboration. I'm sure you saw it in the news. Supermassive black holes produce lots of gamma rays. The center of our galaxy is also a location where there are lots of massive young stars that are forming and exploding as supernovas. Supernova explosions produce lots of gamma rays. The supernovas at the center of the galaxy have been going on for billions of years, and so they've left behind large numbers of pulsars and small black holes. And small black holes and pulsars produce lots of gamma rays. So it's going to be very difficult to present a really convincing argument that any gamma ray signal from the galactic center has to be from dark matter, as opposed to simply being that there are a few more gamma rays than we expected coming from the central black hole or the other black holes or the neutron stars or the supernova explosions. And that is where the dwarf galaxies that I've been telling you about come in, because the next brightest sources of gamma rays from dark matter are expected to be these dwarf galaxies that are closest to the Milky Way, exactly these faint systems that have been discovered over the last couple decades. So if we could detect a similar signal in gamma rays from a dwarf galaxy to what we see coming from the galactic center, then that would be a pretty strong confirmation that that signal must be from dark matter. Because to a gamma ray astronomer, a dwarf galaxy is pretty much the most boring place in the universe. There's absolutely nothing going on in a dwarf galaxy that should be making any gamma rays whatsoever, except perhaps for dark matter particles bumping into each other and annihilating. So these dwarf galaxies don't have lots of black holes. They don't have lots of pulsars. They haven't had any supernova explosions in billions of years. The only thing that should be making any gamma rays is the dark matter. And then, so the people are actively searching for these gamma ray signals towards all the dwarf galaxies that we know about. And so we're hopeful that we may be able to detect something in the coming years. And then perhaps if we can detect a gamma ray signal from known dwarf galaxies and determine what the gamma rays from dark matter actually look like, then we could go out and look at the rest of the sky and look for similar signals in places where we didn't know there was a dwarf galaxy. And that might be one of the only chances we have of detecting completely dark galaxies that would be orbiting our Milky Way, as our cold dark matter theory has predicted. So that's some of what you should be looking forward to in the news in the coming years about dwarf galaxies and dark matter and gamma ray telescopes. And I'd just like to take a couple more minutes and go over the highlights of some of what I've told you about this evening. So we started off by discussing galaxies, how they consist primarily of dark matter. And so you can think of a galaxy as effectively a ball of stars surrounded by a much larger cloud of dark matter that we can't see. We think that this dark matter is a new kind of subatomic particle that hasn't been detected before. And the way that we've been able to study that so far is only through its gravitational influence on the stars and gas in galaxies, which we can see. Our cold dark matter theory does an amazingly good job of describing what most of the universe looks like, except that it makes some predictions about individual galaxies, and specifically dwarf galaxies that have not been confirmed yet. And in particular, it's predicted that there should be many more dwarf galaxies than we've actually managed to find. So with future telescopes, we are almost certain to substantially increase the number of dwarfs that are known. So the Rubin Observatory and larger telescopes like the Giant Magellan Telescope are going to be critical to making those discoveries in the next decade or so. And then gamma ray observatories are going to be essential for trying to detect dark matter signals coming from all of those dwarf galaxies. All right, thank you, and I'd be happy to take your questions.
All right, fabulous. We got plenty of time for questions. I know there's a few in the chat. I don't know if you wanted to read them or I could read them to you, but we can take questions verbally as well. I'll now let everyone be able to unmute themselves. So ask away.
All right, so let's see. We have several questions from Joseph Malik, first of all, do we use the distance to galaxies to trace their evolution, since the most distant ones would be the youngest? Yeah, so that's certainly true. And yes, looking at more and more distant galaxies is a crucial way to study galaxy evolution, because you can study sets of galaxies at different times. The challenge there is that any given galaxy you only get to see at one time, and so we don't get to watch one galaxy evolve over billions of years, and so we have to try and identify similar galaxies at different distances and therefore different ages in order to understand how they have changed through time. I hope that I've answered the question, how do we detect dark matter, in the second half of my talk. You can ask again if not. And then, do the latest equations explaining the Big Bang account for dark matter and dark energy? Yeah, so the current best cosmological model that we have is known as the lambda CDM, where lambda is dark energy and CDM is the dark matter. And as I said, that produces a really great match to almost all of the observations that we've been able to make, except for some of the properties of dwarf galaxies. So Stephen Bedingfield has asked, does the evidence for dark matter, such as the red and blue shifts in galaxies, vary as a function of distance? In general, no. all the galaxies that we can observe in enough detail show evidence of dark matter. It's just that the galaxies that are farther away, we can't observe in nearly as much detail. And so the farther they are, the harder it gets to make those observations. And so that's one of the reasons why we want to focus on the very closest galaxies, because there we can make much more detailed measurements of them. So another question from Joseph, does dark matter exist only in places where a certain amount of normal matter exists? No, dark matter is spread throughout the entire universe. There should be dark matter everywhere, going through your body right now, but also in between galaxies, there's still some dark matter there. Question from Al Kaplan, why do some spiral galaxies have bars, but others do not? That's a good question. It's not something that is fully understood at this point. When we make computer simulations of galaxies, that they basically always make bars, and yet not all spiral galaxies that we observe have bars. And so exactly why that what's known as the bar instability, the fact that a rotating disk will make a bar structure at the center of it happens more easily in these simulations than it appears to in the real universe, is not known just yet, but that's certainly something that astronomers are interested in.
Any other questions?
So I have a question. So you said that we detect dark matter because of the gravity needed to shape galaxies and the way they move. So it requires more gravitational pull to be there. Mm-hmm. So what gives rise to there needing to be more dwarf galaxies around our galaxy? What points to that theory?
So that's just a fundamental property of the way that dark matter particles will cluster together gravitationally. This is not something that was obvious or was predicted in advance, but when people started doing these cosmological simulations of the evolution of the universe with big enough computers, what they found is that you get so as you look at smaller and smaller masses, you get more and more stuff, more and more of whatever structure you're looking at. So there are, for example, our Milky Way has a mass of about 10 to the 12 solar masses. So there are more galaxies with masses of 10 to the 11 solar masses than there are with 10 to the 12 solar masses. Then there are more galaxies with masses of 10 to the 10 solar masses than 10 to the 11 solar masses, and so on down. And so what the simulations have shown is that process keeps on going all the way down to theoretically the mass of the Earth. And so you should have clumps of dark matter with all of these different masses filling the universe. And the smaller the mass scale you get to, the more and more of them there should be. And so for dwarf galaxies, the dark matter mass that we're talking about is on the order of 10 to the 8, 10 to the 9 solar masses, so 100 million to 1 billion times the mass of the sun. And so these simulations have just enabled us to calculate how many of those there should be relative, for each Milky Way that we observe.
Okay, thank you.
Sure.
Excellent lecture.
Thanks.
Anybody else? All right, it does not sound like it. So we want to thank you, Dr. Simon, for joining us this evening. And yeah, it was an excellent talk. We planned this months ago, and I was really looking forward to it, and it paid off.
All right, my pleasure. Thanks for having me.
Yep, thanks again. Okay, everyone, let's go ahead and move on to the open discussion portion of the meeting as we say goodbye to Dr. Simon, although he's certainly welcome to stick with us there. Let me zip through the president's report really quick.
We again still have 280 memberships. That really hasn't changed since the last meeting, which isn't too surprising because this is kind of the wrong time of the year to join, as I'll explain. So again, the question is, can we reach 300 memberships for the first time ever in history? But every new membership that we get is a record holder. Obviously, right now, you can't join online. If you've tried to do that recently, you've noticed the online form has been deactivated. That's because starting on July 1st, memberships will be prorated. So if you join on July 1st or anytime toward the end of the year, you get the rest of this year for free, and then you'll be a member through 2023 or 2024, depending on how long you join. If you do prefer to join online, via PayPal, you can email me and I will give you a reminder on July 1st that you can now join. So we again want to hit 300 by the end of the year. That would be pretty spectacular. Again, if you're interested in learning how to use the Leonard James Ashby telescope in Owl Observatory, email me and we can schedule another training session. We've done one this year, and I know there's at least one member that's interested in the training session, but it's nice to have at least two, but maybe three, up to 4 people would be great. So again, let me know. You can either take it for the first time or do a refresher if you took it once and don't remember anything from the first time. The eclipse planning kind of committee, I guess we can call it now, a committee, has selected or come up with 3 candidate sites for the eclipse. And we can discuss those in greater detail after the meeting. I don't want to announce it quite publicly here yet, because many will be listening on YouTube later, because we want to kind of keep that under wraps for the time being. But we can discuss it in a little more detail once we stop recording here. But we do have 3 sites that we can look at. 2, I think, are strong contenders. The other one, not so much. But we're working on it. We have many outreach opportunities again, which is the first time we've had any in a while. The Air Zoo has again invited us to their space camp on Monday, June 20th from roughly 1:15 to 2:15 p.m. And they mainly want solar observing. So we need people with a solar telescope to volunteer. We really just need maybe 2 people. Usually Roger and I have done it in the past. But, some people may be leery about COVID, but again, we'll be outside in the open with just really maybe 20, 25 people. But again, you have to either have a white light or hydrogen alpha telescope would be preferred. The Pierce Cedar Creek Institute has invited us to their family science night on Wednesday, June 22nd from 6 to 8. I've been asking for volunteers from that, but haven't heard from anyone. They prefer us to do a hands-on activity in their tent. But if we can't find anyone to do a hands-on activity, then maybe we can at least do solar observing, and I can at least do something myself. But again, it's good to have several members there. And we have the Kindleberger Festival on Saturday, July 9th. And usually that runs from 9 to 3 p.m. We basically there, we hand out literature, NASA freebies, and we can do solar observing as well. I don't know if Jack wanted to add anything, but again, we usually need at least a few volunteers to that.
Yeah, 3 or 4 of us is a good number. That works well. Sometimes the crowds are large and we get busy, but that's always a fun event.
Yep. Okay, so we are looking for volunteers for those 3 events. If you didn't write them down, they are in the newsletter. Just look toward the back on the announcement page. There's a little ad for the outreach opportunities there, and we definitely need people. I'm still looking for speaker ideas for the 2022-2023 Astrophotography SIG meeting. I got to say, recently, I made up a list in my head of the reasons why we should continue the SIG and the reasons why we shouldn't continue the SIG, and the reasons not to do it were a lot longer than the reasons that we should. The strong reason for me why we should is I would like to try to do them, in person, because we couldn't do it this past season because of COVID. But again, another reason why we shouldn't do it is because it's just another thing I get stuck with doing all by myself, and I really don't want to do that. I take on too much as it is, and so for the SIG for sure, I'm looking for input for speakers. So if I don't hear from anyone in the next week or so, I'll kind of make a decision one way or the other. And then we recently had a email. Let me see if I can bring it up here and read it to you. So I got an email from a gentleman named Jim, and he says, I have a telescope that my brother built. I'm willing to donate it to your organization. The build with the camera took several years. He passed away. It is currently in storage, and I would like to send you a picture. So he did. And he gave me more information here. It's a Cassegrain style telescope. And let me try to share the screen with you so you can see a picture of this thing. So it should come up here, unless the thing crashed on me. But I can zoom in here a bit, and you can see it does look like a Cassegrain. It looks, they said it's built, but it looks like a manufactured one to me. So if he did build it, he did an excellent job. So it's mainly set up for imaging, but it's a Cassegrain style, so it should be an excellent planetary scope as well. And there's lots of stuff here. He was willing to donate this to the KAS, so the KAS can take it as a donation. But frankly, if any member wanted to, perhaps just take it, or perhaps give the club a small donation, either or would be good. But I just wanted to mention that. But man, it looks like quite the complicated setup. So there's that possible telescope out there that you could either, maybe what the board decides. Maybe the board can discuss it further. If we get lots of offers to buy it, we can take it as a donation and sell it off to someone as a fundraiser. Or if we don't hear from someone, maybe we can just give it away. But it sounds like that telescope needs a home. So that is all I got for the president's report. Are there any observing reports or even imaging reports? Jack.
I actually happened to be up early enough this morning to look outside, and through the groove between the trees, I saw at least 2 of the planets that were up. Beautiful, clear, gorgeous. Not being able to see the whole sky just through the window, I couldn't tell which of the planets I was looking at. I'm thinking Venus and Mars, but I'm not 100% sure which I was looking at. But it looked really wonderful. I've got to be out early tomorrow morning. I'll try and look and see if I can't see the whole bunch of them.
Yep, I was going to mention that it is tomorrow morning where you're supposed to see all the naked eye planets together in the kind of southeastern sky. If you do live in the Kalamazoo area, a great place to go if you have trees is Richland Township Park. There's very little obstruction from trees there. So that is a great spot to go if you want to see all the naked eye planets at once. Uranus and Neptune are there too, but you need optical aid to see them. And even then they'd be tough to see because you really can't enjoy this until dawn. So I sent out an email about the Tau Herculeus meteor shower, and I was the only one to show up at Richland Township Park. So the reputation of the KS as not being an observing club is still strong. Boy, it's still going there. But it's not too surprising because, it was Memorial Day. Everyone was probably out and about and busy. It was last minute and everyone had to be to work early the next day. But, I went out for just a couple of hours and I saw about 10 definite tau Herculeans. They're all very slow, short-moving fireballs, none brighter than first magnitude. They kind of range from first to third magnitude. And I saw one definite sporadic bolide that wasn't very bright either. But there was definitely a meteor shower, but it was nowhere near a meteor storm, which, again, didn't surprise me at all. But it was definitely worth going out. The best one I saw was low in the south toward Scorpius, and many of them seem to have a very orangish color. So if you didn't go out, it was definitely worth it. You definitely missed a nice little short bolide show. A few weeks back, when we had lots of big sunspots, I did take my solar scope out, my own personal solar telescope. And for the first time, the sun was actually worth looking at. Lots of sunspots, lots of prominences, lots of filaments. So I'm anxious to get my solar scope back out, or even better, head out to Owl Observatory and try to take some images of the stuff, or we can just view through the H-alpha scope in there. And if I do head out to do solar imaging or whatever, I'll try to let everyone know, and you can join me out there. But yeah, I've been trying to get out and do some observing and imaging, and since no one has really reserved the scope too much lately, I've been using the remote scope out west a lot. So it's been collecting photons almost every night, except Monday when I went out to observe the meteor shower. I didn't use it that night. Plus, it was a little too windy out there anyway. But the remote scope has been used a lot, at least by me. Any other observing reports? Observing club.
Well, you know,
yeah.
well, Richard, if people want to wait to the end of the month, the last Sunday of the month, all the planets will be lined up again, because they'll all be in the pre-dawn sky, but the moon is going to be between Venus and Mercury.
Yep, that's right.
And Saturn will be on the far right, and Uranus and Neptune are in between. So you would get all 8 planets plus the moon in one shot.
Mm-hmm.
So the moon should be a nice crescent at that point too, which is always cool.
Yep. If you are up early and have a camera, take a picture and we can put it in prime focus, because that'd be pretty cool.
That's my plan.
All right. All right. If there's no more observing reports, we can move on to astronomical news and events. I already wrote about it in the newsletter, but I hope everyone saw the image of Sagittarius A star, which is a nice orange donut. But when you know what it is, it makes it much more special. But you know, the image itself isn't terribly spectacular, but you got to use your mind's eye too. Any other news out there?
First image from the JWST is scheduled to be July 12th.
Oh wow! Okay, they even have a definite date on it, huh?
Yep, they just announced that 2 days ago.
All right, July 12th. That'll be pretty cool. And I did see, I've been teaching for years, you know, because Uranus and Neptune are almost exactly the same. You know, Neptune's a little more massive than Uranus, but, you know, they're very similar mass, very similar size. But of course, Uranus is a much lighter blue than Neptune. And for many, many years, I've been teaching that it's because of the difference in methane between the two planets. But it sounds like that's wrong. So it sounds like there's a haze in Uranus's atmosphere, you know, in the upper atmosphere, that makes it look a lighter blue than Neptune. So that was a recent announcement from the Hubble Space Telescope people. So I have updated my lecture. If I ever do talk about Uranus and Neptune again, I will no longer mention it's the difference in methane, because that has been supplanted by the new announcement. So that's not the first time I've had to change my lectures over the years from new discoveries, but it won't be the last, especially with the Webb telescope out there. Any other news? Oh, I also did hear the InSight mission at Mars is almost over, because the thing has accumulated lots and lots of dust. So it's about out of power. No dust devil apparently is going to hit it and clean it off again. That'd be nice.
Nope, they have not been lucky that way.
Yeah. All right, so moving on, since we're not going to have a meeting in July, I thought I would run over all the events for the summer. So of course, tomorrow, we're supposed to have a public observing session at the Kalamazoo Nature Center, and I'm pretty sure we're going to have to cancel based on the current forecast, but I will publish the notice on the website and via social media as soon as we make an announcement about tomorrow night, but it is not looking good. But we have another chance on July 18th. And then, of course, we have sessions scheduled for July 9th, July 23rd, August 6th, and August 20th. And if you just want to observe in a smaller group with club members only, we, of course, have the Observing SIG. They'll be at Richland Township Park on June 25th, July 19th, August 25th. And, of course, we have the Garden Getaway. Dave Garden, I don't know if Dave is still with us here. Yep, Dave's still here. He's just not sharing his sound, but.
Yeah, I'm here.
There he is. Oh, there he is. You're so dark, I couldn't see you. You could probably open the roof now. But Dave has invited us to his property within the Huron-Manistee National Forest. And he says he has room for maybe about a dozen of us. So, of course, you know, Dave's primarily an imager, and so it'll be mainly imagers, but I'm sure we can squeeze in some observing people too.
Oh, yeah.
You know, while those of us that are imaging, we can spend time looking through your telescope for those that are there just to observe. So, Dave, is there anything else you wanted to mention about your property and the?
I say you'll have to do camping or trailers. I have room for about 3 or 4 mid-sized trailers, plenty of places to pitch a tent. I'll have my cabin open to the restroom, kitchen, stove, or whatever. Just walk in all day or night, whatever. Yeah, it'll be a good time.
If it's clear.
Yeah, if it's clear.
That's always the big if, but yeah, I'm looking forward to going up there if it's clear.
I'll be up early and staying late.
Yeah, me too. All right. So Prime Focus, I hope everyone is enjoying the series on Robert Burnham Jr. I know part 2 was the good part where things are going well for him, but starting with part 3, things kind of go downhill from there. So if you don't know much about the life of Robert Burnham Jr., prepare to get a little depressed there if you're enjoying the series. But again, I'm always looking for contributions. It can be an article about your favorite subject in astronomy, observing, maybe you go to a star party or a astronomy museum or planetarium, you can write a report about it. We're always looking for stuff like that. Or again, you can just share your latest images. You know, I shared images from Pete Mumbauer and Eric Schrewer in the latest issue, and I hope you enjoyed those. I know some of you didn't enjoy printing them out if you did, but you don't have to print that stuff if you don't want to. So again, the newsletter lives and dies by contributions. Is there anything else that anybody wanted to share? Don, is that you whispering there?
Yeah, my lips tend to move when I read. So.
Oh, okay. But you had nothing to share. Okay.
No, I was reading my email while I was listening.
Okay.
To be truthful.
All right. So it doesn't sound like there's anything else to share, right? We'll give everyone another chance there. I know some people chime in a little late.
I just want to make sure I heard right. You want an email to confirm whether you're going to help out at the Pierce Cedar Creek or Kindleberger or any of the others, right?
Yeah, email's my best way. You can email either me or Jack for Kindleberger, because I won't be doing Kindleberger, but I plan to be at both Pierce Cedar Creek and the Air Zoo.
So I can help with all 3, but I'll send you an email to confirm that.
Okay. That would be spectacular. All right, again, for the first time, we're not going to hold a July general meeting anymore because turnout was always low, at least, you know, low for us, maybe compared to some smaller clubs in the area. We actually have good attendance, but for us, it's kind of on the low side. Most members don't really seem to appreciate gadget night very much, but in 2017, we didn't do any events in August at all. So we kind of combined the July meeting with the picnic, and we did gadget night during the picnic, and I really loved it. I thought that went a lot better. So we're going to do gadget night during the picnic from now on. We might hold the occasional July meeting if we have like a special topic or a special speaker. Like in 2019, we had a meeting on the Apollo program that was well attended. But for the most part, July is going to be observing. That's it. So
let's hope so.
Yep. Well, yeah, we do hope so. But in August, we're going to have our annual Perseid potluck picnic. I think this is picnic number 27 or so. I've lost track of how many Perseid potluck picnics we've done. But this year, we're going to be at Van Buren State Park on the shore of Lake Michigan. And we will definitely send out an email about that in the future. We do have a grill out there at our picnic site, but we are looking for a volunteer to bring a grill to cook again. I know Andrew Lovelitz there did it last year. I don't know, Andrew, did you want to volunteer your grill again this year? All right, I see a thumbs up, so we'll take that as a yes.
Yep, it's portable. I'll be there.
All right, great. So
Thanks,
we will count on you to do that, and hopefully Don will buy everything, including cheese this year.
Yeah.
Because he forgot the cheese last year.
Yeah, I almost had cheese between my ears. I forgot it. I don't know. Yeah.
Swiss cheese, obviously, because it went right through the holes.
Yeah, went right through.
So we are hoping for a spectacular turnout for the Perseid potluck picnic at Van Buren State Park. Apparently, we can arrive much earlier than our usual 6 o'clock start time. So if you want to show up a little early, maybe we can do a little solar observing. We can walk along the shore of Lake Michigan. We'll throw Jack in, see if Jack can swim.
Go surfing.
Yeah, we can use Jack as a surfboard. That'd be fun. Just
No
kidding.
comment, Jack?
I think Richard would make a better surfboard than me.
Nah.
Yeah.
I'd see.
We'll just use Richard's telescopes as flotation devices.
I don't think that worked very well.
Well, Jack, he would work better because he's more full of hot air than you are.
That's true.
Hey.
I wasn't going to say it, but I'll agree.
All right, we're done. We're done Richard bashing. So if there's nothing else, we will go ahead and officially conclude the June general meeting. The sun is still up, so go out and enjoy the weather.